Entonces me evita el que pueda hacer el trámite.
Ahora, ok. Vale, ahora sí que estamos. Okay, welcome to this new session of the Thimne Coffee Talks. Today we have with us Cecilia Soriano and Eva Pérez. I think that Fernando Salazar is going to be involved also. And they're going to speak about the Challenge 3 of the Biblates project, which aims to design objective tools to help air quality managers in a given region to predict the incidence of episodes when tropospheric, we will know what it is, ozone emission concentration exceeds the legal concentration limits of ozone. So thank you very much, Cecilia. I think you're starting. Go ahead. Thank you very much.
Okay. Yeah. Thank you very much, Alejandro. Yes, we are continuing in this series of cafes related to the Pipelaters program, this platform pilot for support for predictive flood management and sustainability. And there are several challenges in this project. Now, today we deal with challenge 3 related to ozone. 2 weeks ago, we had the presentation of Ignacio de Pauplana about simulation in meteorology in urban cities. No? Now we are dealing with ozone in cities and in general. No? Before starting, as you said, we have also here with me for helping me in this presentation. We have Eva Pérez, who is the head of the service of emissions at the Direction of Prevention and Control of Quality of Air Quality. And with her, we will start with a short presentation and explain a short words regarding to the needs of the department regarding ozone, and then I will do a presentation with some context of ozone in air pollution management and more details of the project that we are developing. And finally, Fernando Salazar, we will have some time to describe with more detail the tools in machine learning that they are developing for this project. So first, Eva, if you are ready, I would like you to give us some words regarding this challenge that we deal with. Thank you very much.
Hello. First of all, I would like to thank Thimne and Xavier Baulias to invite us to participate in this project. Tropospheric ozone is one of more important issues in air pollution in South Europe. Ozone air quality assessment in Catalonia shows almost all air quality zone, almost all Catalonia register ozone high background concentrations. And also air quality monitoring stations located in suburban and rural areas at certain distance from the emission of metropolitan area of Barcelona, downwind following, register peak ozone episodes during the spring and the summer. On the other hand, European legislation established the mandatory to inform citizens when there are exceedance of ozone threshold. Because of all these reasons, the Ministry of Climate Action, Food and Rural Agenda of the Government of Catalonia needs tools to improve ozone concentration forecasting and to set accurate policies to reduce ozone levels. Thimne is developing a statistical model for forecasting ozone levels at the monitoring station using machine learning. We hope during this year this system will be operative. Thank you very much.
Okay, thank you very much, Eva. Indeed, this is a complex problem, and it's complex enough start this presentation with explaining by my side some ideas, some context, just to start to know well what we are dealing with. So I will start first with this explanation of some data and curiosities regarding to ozone, and then I'll explain with more detail, which is the flow that we are following, the workflow that we are using in the project. So as I said, first of all, we acknowledge all the people that is working in this project. As you can see, and as we mentioned, it's a multidisciplinary group with very different knowledges. The coordination is coordinated by Eva Pérez and Sofia Baulias in the Generalitat, and by myself in CIMNE. Then we also participate from CIMNE, the machine learning team, with Fernando Salazar, David Vicente, Sergio Lopez. We have a collaboration, very interesting collaboration with the climatology team of the University of Barcelona, led by Javier Martín Vide, the Professor Javier Martín Vide, Pere Esteban, and Marc Nemus. The group in the team in METEOCAT is the group of the subdirection of prevention of forecasting control air quality, and it's that with Eva Pérez, with Cristina Alonso, Xavier Guinart, and Isabel Hernández. And last but not least, we have from CIMNE the group of web and platform team that are the responsibles to do all the infrastructure and all the hardware and all the platform that we need to put all this project together. So now I go already to my presentation. As I said, what is ozone and why and why we talk of good and bad ozone. This has to do with these difficult words, the stratospheric and tropospheric, that you mentioned before, Alejandro. The good ozone, the one that is good, it's the tropospheric ozone. This ozone is the one that, if we look at the profile of the different parts of the atmosphere, it's the one that we can find in between 20 and 30 kilometers, and it's the ozone that is related with the ozone layer. Therefore, it's a good layer because it prevents of having ultraviolet radiation into the atmosphere, and that would arrive to the Earth, and that would be bad. No? So that's why we talk of good ozone, this stratospheric ozone. No? The bad ozone is the one that we call tropospheric ozone, because it's situated in the tropospheric part of the atmosphere, which is this part. Oh, sorry, I just record that they told me that there is this laser. Okay, this is nice. So tropospheric ozone is the one that we find directly on top of the land, of the Earth, and it occupies the first 10 kilometers of the atmosphere, and it's bad because it produces irritating reactions to the people, and also the people who have respiratory difficulties. That's why we talk about good and bad ozone. The one that we deal with is this one in our presentation and in our challenge, the tropospheric ozone. Let me start with explaining which are, or with introducing to you which are the main sources of air pollutants. We're talking here of air quality and therefore the air pollutants that are in the air. No, which are the main sources of pollutant into the atmosphere? Well, we can divide these the sources of pollutants between natural sources and anthropogenic sources. Natural sources are sources such as those after a volcano eruption, a fire in a forest, or dust storm in the desert. Those are natural sources. Anthropogenic sources are those that are done after actions done by the population, and the most typical ones are industry sources, traffic, heatings, and in houses, and also cattle and agriculture. The main pollutants that release these different sources are carbon monoxide, nitrogen oxides, sulfur dioxide, particulate matter at different ranges, and methane. But here we don't find ozone as a source of air pollution. Why? Well, what's the deal with transport ozone? Why don't we find in this list of pollutant sources? Well, the fact is that the tropospheric ozone is not emitted directly by any source. And that's why we call it a secondary pollutant. It is formed after a complex photochemical reactions within intense sunlight. That's why this is interesting. If you don't have suns, if you don't have radiation, the reactions that have to occur for the formation of ozones wouldn't be produced. That's why we hear of episodes of incidents with ozone only in spring and mainly in summer, when the radiation it's higher. No, the main reaction that has to be be conducted to produce ozone involves nitrogen oxides that are emitted by combustion sources, such as cars, for instance, and VOC, volatile organic compounds that are emitted by vegetation, by solvents, for instance, and other chemicals. Without these VOCs, we couldn't be able to produce ozone. But it is clear now, I guess, that ozone is not emitted directly to the atmosphere, and that we need some precursors. In this case of ozone, nitrogen oxides and VOCs, to produce this ozone. The chemical of the atmosphere is complicated, but the main equation or list of equation and the main process is the one that we describe in this reaction, where we describe the main equation dealing to the formation of ozone. No, the first three equations of this list are the ones that describe the formation of ozone from a molecule of NO2, there with the help of the radiation. This molecule breaks, and together with this oxygen produces at the end a molecule of ozone. Okay, this is a system that is approximately in equilibrium because this ozone is reacted with NO and disappears for this for the formation of this new NO2, and therefore start again with this these three equation of formation and destruction of O3. And that's why we say that this system is approximately in equilibrium. Right? Only if we wouldn't have NO on the lag, if we don't have NO, it's the only possibility that the ozone would increase. So why? Which is the situation for to increase for the increasing of ozone and arriving on an episode? So the situation is that we enter and we put together the NO with box, with the vegetation. So in atmospheres that have VOCs, particularly, for instance, in forest, that it's a source of this kind of compounds. Well, so in situations in places in the territory where we find box, the radicals that they emit bring or convert the NO to NO2, and therefore this NO cannot participate in the system that we had at the beginning, that was approximately that was in equilibrium. Therefore, the situation is that NOx instead of breaking the ozone, NO2 contributes to the net formation of ozone, and the final result is that there is an increase of the concentration of ozone. No? This is complicated because the atmospheric chemistry, as I said, it's complicated, but the idea is that if we have an increase, an area with VOCs, and this VOCs get in contact with NO2, this produces an increase of the concentration of ozone. Which, sorry, I cannot. There's it's more complicated indeed, no? Because the situation is that under days with very high radiation, so days where ozone can be produced because we have radiation normally in summer, we comparing the city and the country, we find what seems to be a paradox, and the fact is that there is more ozone in country than on cities where all the pollutants were emitted. So as I said, in the city, what we have is a high concentration of NO, and this concentration of NO breaks the molecule of ozone, as we show when I show you before in the reaction equations. No? However, in the country, it's the contrary. As we move, and the fact is that as we move away from large urban centers, the ozone precursors, particularly the COVs that are emitted by vegetation, increases, and O3, the ozone, builds up. No, so as I said, the result is that in the highest levels of tropospheric ozone is recorded downstream of large cities. No, apart of having more quantity, despite of emitting of more the pollutants in the city, the contamination of ozone it's only encountered or produces, it's only produced in the country. No? We have an example of this reason of more contaminants in the country than in the city. And then I can show you these simulations. This is only a mesoscale simulator with the transport that we have created artificially in Barcelona. And what we have done here is to simulate the transport of this source along the time under the situation of what we call a barometric swarm, which is a typical simulation during summer, where the synoptic or large scale meteorology is very calm. We have the isobars very separated, so the situation is very tranquil in the sense of the movement of the air masses. No, so the more important are these two slides that show the dispersion of this source that we had at the beginning of the simulation. And indeed, during the day, as the difference of temperature between the soil and the sea increases, the circulations of mesoscale circulations and start, and one of these mesoscale circulation is the sea breeze. No, so you can see that at the beginning of the morning at midday, these emissions that we had released in the morning start to enter into the land because the sea breeze sweeps this pollution. No, and later, even in the afternoon, we can see here the location of the plume at 6 hours, still with the breeze has been located perpendicular to the coast, and we see the intrusion of this pollution to the interior of Catalonia and towards this area, big or la Bages, Comarca del Bages, and the important thing is that this plume goes with and flies with loads of pollutants inside towards areas with vegetation, and that's the cause that in this area of Big, it's very usual that in summer we can find episodes of ozone that we don't find in the city. No, so what are the tools? So the idea up to now is that, well, yeah, ozone is difficult. Also, yeah, and ozone, it's difficult to deal with, no? To prepare plans and ideas to try to minimize, no? So, which is the main part, the main tool that that manager, the air quality management uses when they have to decide or to need tools to work to make predictions. No, that this is one of their duties. No, we talk then of air quality models. So this is the main tool that they use, an air quality model is a tool that relates the emission of pollutants that are released into the atmosphere, and they related them to the emission concentrations that that are receptor, for instance, the person in the street receive. No, so air quality models serve to, given some emissions, learn to know which are the impact on the population, no, through the concentration, the emission concentrations that they give as a result. These models, in general, can be described with in three parts, main parts. One is the meteorological module, when we do all the simulations and all the formulations related to meteorology as a fluid. Then it also needs an emission module indicating all the sources that play and that are emitted, that then had to be transported to calculate the final pollution. And the third module is this dispersion or transport module that give information about how the emissions disperse along the territory. It can have, and that in general, if we are dealing with ozone, we'll have also a chemical transformation module to deal with the ozone and have information about ozone. In general, which are the elements relevant in an air quality model? Well, as I said, what we are dealing here is meteorology and air quality managing at the regional area, so a scale. So this scale is what we call the mesoscale scale. No, so in air quality, in general, we talk and we deal with models in the mesoscale, which main characteristic is that they have to give results in very little space and with very resolution. And to do this, what they use is the technique of nested grid. That is, to arrive to the definitive information and data that they will explore in terms of air quality data, they start from a domain higher, more bigger, and from there they do different simulation. In this case, for instance, from 15 with a resolution of 15 kilometers up to 1 kilometers, which is the latest result that we will receive. No, so we go after one, and from each from the outer domain, we introduce all the different boundary conditions from one to another presentation, the simulation, up to the domain that we are interested to analyze. Which are the information that we have to introduce in this air quality model at regional level, at the mesoscale? Well, we have to enter and introduce boundary conditions that will come from synoptic scale models, the type of models and maps that you see in the TV with deeps and lows. No, this probably can be download from the ECM field, the Center for Medium Range Prognostic of Meteorology. We put this information in the as boundary conditions. What else do we need? We need information also about the orography and land uses, because land and the sea and the atmosphere change energy, and we have to know exactly, depending of the land that we are on, this exchange of energy will change. So orography and land uses, that's also another thing to take into account. What else will we need? We need emission inventory. So we know in the session that we are studying, we need to know all the emissions that of pollutants that are released in my region. So this one also is an input to my program. And finally, if we are dealing with our ozone, we'll have also to have a module dealing with photochemistry in the atmosphere, for at the end to get some results that give us the emission concentration at every cell of the area that we want to study. So it's a big deal of work, a lot of simulation, and that's why to do this we have to use large computational resources. We have to do that after, well, we have been the community of meteorology and air quality. It's one of the most has been working more years in this area, no? So in general now, after so many years, we are starting to see that they work well and they will have good performance, and after validations that are very accurate. There is a drawback in these models. One has to do with the accuracy of immission. We can have the best model for meteorology, the best model for transport, but if we don't have the emissions that are included in this atmosphere, we will have a lot of error in this in the simulation. And the other thing that maybe it's also a drawback of this type of models, that there is little interaction with the manager, the air quality manager. After all, they just receive some maps, and from there they get their prediction, no? In fact, working with the people of Generalitat, who are day after day dealing with quality, with air quality, there are some needs, no, that air quality managers would like to have. Well, we will have tools that require small computational resources. These simulations in these resources must be, however, operational. That means that for decision taking, we need to have the results 24 or 48 hours ahead of the day that we are predicting, no? And for another thing is that they would like to have capacity of interaction with the model, no? To have some APIs, some possibilities of interacting with the results, and think also that they will be useful to investigate these future scenarios. So all in all, this was a little bit the idea that brought us to this new approach that we are doing in project pipeline, no? Different ways of helping quality air manager to do their job and inform and try to forecast better and minimize the impact of ozone in the people in general. So going back now to ozone, what we want to do now, it's still working with ozone, find new tools that can help in managing ozone, no? And that for us is it's a challenge in by itself. I call it the data challenge because it's a different way of approach to air quality. It's a challenge. It's an approach based on data science, and I put here with a twist of meteorology because it's true that for a person that has worked many years in simulation and working with the equations of the fluids involved and several and energy balances and things like that, going only to the raw data, it's difficult, no? So we'll try to maintain a twist on meteorology by using and by working also with meteorology synoptic data that will some way make us see if the possibility of describing a model of based on changes is reasonable or not. We don't know. For this, what we want to do in the project that we are working of ozone, it's designing objectives to help air quality managers and to predict the incidence of episodes. That's what we want. Just new tools to help air quality managers. And the idea is to try to have information so that when tropospheric ocean emission concentration exceeds the legal concentration limit of ozone, then we can act in some way, no? With this new approach will be based on data, meteorological basis. Also, we will talk with air quality data, other data that we can think that can be useful, like for instance, traffic data if we had it, and also the synoptic situation. We believe that the synoptic situation, the situation related to the main systems in the that occur at larger scale can be done somehow correlated with the emission of ozones that we suffer, no? For this, what we want to do is to identify meteorological situations that lead to episodes of ozone pollution. Also, we will to identify areas, particularly in Catalonia, of regions with ozone incidences only under severe weather conditions. We would also to evaluate which variables play a relevant role in ozone production scenarios and each measurable point. And finally, we would like, at the end of thought, is to predict. No, we want to predict situation of exposure to the population related to air quality and particularly to ozone. For this, we have this solution, or we have proposed this solution based on the yellow, green, and blue boxes that were defined in by the PyPLATES coordinator. The yellow box is related to input. The green box is related to models, and the blue box is related to results. Regarding inputs, the input data that we will use in the model will be air quality data, this pollutant, meteorological data, reanalysis data. This is the data of the synoptic, so larger scale maps that we see on the TV every day. And actually, they are just surface pressure maps. And we will collect them also to relate them to the other data. And another derived variables like work, holiday, or atmospheric stability that also is interesting in terms of meteorology. Most of this data has been downloaded from databases of La Generalitat and METEOCAT. As regarding models, we have a synoptic classification that I will describe next in the next slide. What we will do is to try to clusterize, find clusters among different situations at the synoptic scale to identify different types of weather, of synoptic situation. And then other models that we introduce is the machine learning model that is developed in Python that we are using to work in machine learning all this data that we have compiling. The data that we have compiled comprise 20 years of data. So we are dealing here with a large quantity of data. And finally, the blue box is the box of the outputs of the results that we will obtain when we run this tool. The types of results that we will receive are records. So, for example, the maximum value in 24 hours of ozone, or the hourly values of ozone, depending, and also can be classes. So, for instance, levels or limits between several values that are designed according to the legislation. They cannot be lower than 180, or they can be between 180 and 200. These are classes. Okay. As I said, in the green box, one of the models of the tools that we will introduce has to do with the analysis and of the obtention of synoptic classification. What we want to do is to try to find some groups from a big collection of individual maps of atmospheric circulation maps during a manual or an automatic method. We do some grouping, some clustering, and at the end of this work, we obtain a catalog with different case groups, with different. So what we have done is to cluster all the different situations that we can have during 20 years. Okay. This is the example of one of these classifications that we have done at the synoptic situation. We have done a classification only using months May to September, because since we are working with ozone, probably it will make sense to work with data only from this period. That is the period during which the ozone episodes are more frequent, and it wouldn't be useful for the winter to use this. And these are the result of this classification of this clustering group. So we have a cluster that can be described as advective. This other one, anticyclone advective situation. and this synoptic situation can be described as cyclonic. So once we have this classification of these synoptic situations for 20 years, what we have to do is to introduce this data into the machine learning model that we are developing. So at the end, which is the calculation engine at the end, which is the flow that we are the flow work that we are following in this project. For a start, we have in external servers data of METEOCAT and data or meteorological data from METEOCAT and data from GenCat with all the air quality data. We have downloaded the historical data series, all the information, all the data, and we have developed, or we are developing, a model conformation and training and validation of this machine learning that we are developing. Have to say that in this machine learning data, as I mentioned, we only not only use data of meteorology and air quality, but we also introduce as a variable the type of synoptic situation of that day. So synoptic situation, those clusters that we have separated in the classification. This information is included together to the information of all the days that we have put together in this model. No, the finalization after doing the training and the validation, we have already a trained model. At the same time, we have worked with EPIs in order to be able to download all the all the data, both meteorological and of quality that we need for the project. And the data flow, when the flow of the work to obtain the results that we are dealing this, would be that we would at the 2 days before or 1 day before the date that we want to predict, we have data pronostics by the European Center of Large Prediction, and together with this data, the meteorological data and the series, we download that information every day. We introduce this information in the template platform, where the integration, we have done the integration of all the calculation models, and with all the download data that we have, and together with the models of machine learning, we are able to produce some results in terms of visualization and results of values, and also we also have developed a user interface to try and to be able to take more information that the manager needs in his work. No, and I think that with this I finish my presentation. And now Fernando will explain a little bit more in detail some details about the machine learning developments that we have done in this project. So I will leave my presentation, I think. Let me see if I am able to do this from here. And I think that now you have the flow, Fernando, to continue with the with the part of reality.
Okay, I'm going to try to share my screen. Okay. Okay.
Okay. Ya te vemos, Fernando.
Okay, so I start from the same slide that Cecilia was mentioning before. This is the overall workflow. Well, I'm going to focus more on the machine learning part, as Cecilia said, and in particular, we provide more information on the steps that we have developed more at this stage of the project. You know that this is a project under development, and we have this part, and I will go to every of these steps. So first, we have downloaded information from METEOCAT and from METEOCAT regarding air quality and weather and meteorological stations. We have as many as 49 air quality stations and 191 meteorological stations. A lot of information there. So, well, this is a work to be done to download, to put together, to clean all this data, etc. Then, regarding the development of the predictive models, first of all, we have to check the quality of the data that we have. We have different recording periods for every station. We identified emission periods without data. We are exploring options to fill this data that we don't have. And we are also thinking about how to associate air quality and weather stations, because when they are located in different positions in the territory. So since we are using meteorological data to predict air quality, we need to decide which weather stations to use for every air quality station. Then we have to define the prediction task. We want to predict the ozone levels, but this can be obtained in different formats. First, we are evaluating or analyzing models for predicting 1 and 2 days ahead. And also we are assessing the efficiency of our models to predict ozone levels both as a numerical value and as a categorical variable. This means that we transform the numerical value of ozone concentration into, in this case, 3 categories: low, intermediate, or high. We have been using so far the random forest algorithm for this model. I will say a few words about it. This is, well, with a little bit more detail, the data we are handling. I won't stop too much here because Cecilia already mentioned this. We have these meteorological variables together with the synoptic situation. We check this as an additional ordinary input to our models. We take also air quality indicators together with the ozone concentration at previous dates. So we want to predict the ozone level tomorrow. We are going to use the ozone recorded today. We saw already that ozone levels have some inertia, so there's a strong association between ozone concentration today and that tomorrow and the day after tomorrow. We also use other variables such as the overall time and also the calendar day, as Cecilia mentioned before. So we put all this data into our machine learning models, and we develop, as I said, different versions of our predictive models to predict ozone concentration, either the hourly maximum, the maximum in 8 hours, or the categorical level of So we have chosen random forests algorithm. You know, machine learning, there are a lot of different algorithms that can be used, and it's not clear which one is better for every problem. In this case, we chose this one because it's easy to calibrate, meaning that there's just a few parameters to modify to have a predictive model. And also because it's robust in the sense that the parameters that need to be calibrated have a low effect on the overall result. And also because the random forest perform some sort of automatic variable selection. This means that you can put a lot of different inputs variables there, and the algorithm automatically selects those inputs which have an influence on the result and neglects those which don't have an influence. This is an interesting feature of this algorithm that in this particular case, because as Cecilia mentioned, this is a complex phenomenon. It's not clear which are the most important inputs, which are the precursors, and how it works. So we wanted to put as much information as possible and let the algorithm to select which variables play a relevant role. Also, the same algorithm can be used both for regression and for classification. This means for predicting the numerical value of the concentration, and also for this categorical low, intermediate, and high variable. And the algorithm has automatic or built-in functionalities to compute the importance of the variables and the average effect of every input on the response. And as we will see later, this has been useful to us to provide information to the users regarding what's happening and why this is happening. So far we have performed a preliminary analysis for which we took two couples of stations. You can see here, the red dots are air quality stations and the green ones are weather stations. So we predicted the ozone levels at this Palau Real and Exemplar in Barcelona City. And for that, we took as inputs the weather data from this, the closest meteorological station, as you can see. We took 20 years of data for training, and we also evaluated two different approaches. One involved trying to predict the whole year, the same model for predicting the ozone level during the entire year, and the other one focuses on the summer months. As mentioned before, this is where the ozone levels are higher, in general, between May and September. Well, this is something that was done as a preliminary analysis. Now we are working on extending this approach to all Catalonia, and for that we are evaluating other approaches. The first one is the one mentioned before. We take the closest meteorological station to the air quality station that we want to compute the ozone level. The second option will be to take more than one meteorological station, say, for example, all the weather stations at a certain distance from the point where we want to predict the ozone. And the third one is based on the air quality areas. These areas, these polygons defined here, these are defined by the Generalitat de Catalunya according to the properties in terms of air quality. So we are also evaluating this approach. Well, these are the results of this preliminary analysis. We can predict, compare our predictions with the observations, and we can take a look at the influence, the relative influence or the importance of every variable. Here we can see, for example, that the previous value of ozone is the input that is more associated to the forecasted ozone concentration. And also we have here the average effect of some inputs on the ozone concentration. In particular, we are looking here at different moving averages of the NO2. So, regarding, once we have the model, we have downloaded our data, we have done all these evaluations. Once we have this trained model, we want to use it not to answer these 4 questions that were raised by the end users, the people from the quality department in METEOCAT. So the idea is that Pipelets platform, as you know, is helpful for the policymakers, for managers to handle, in this case, the risk of high ozone levels. And for that, they wanted to have information to answer this question. What is happening with ozone concentration? What will happen, and this is the most important one, what's going to happen with ozone tomorrow or the day after tomorrow? Then the model can also be used for predicting what-if scenarios. What would happen if this or the other input would be modified? And finally, why is it happening? What are the variables that have a more important influence on the ozone concentration, so that we can think of solutions to try to alleviate this problem. So we analyze the models to draw information to answer these questions. So for the first question, what is happening? In fact, here we are not actually using the predictive models. Instead, what we're doing here is to put the information available, the records, in a format that is easily visualized by the user. So we show here the historical data, the number of episodes of high concentration of ozone per year, average historical data, etc. So we are transforming, processing the information to put it into the tablets. Regarding the second question, the most important one, what will happen? Here we check the actual values for the inputs, the temperature, the solar radiation, etc. And we put that information into our models, generate the predictions of our models, and in different formats, 1 to 2 days ahead, and numerical or as categorical values. This answers the second question: what will happen tomorrow or the day after tomorrow? As for the third question, what if scenarios, we can use the same predictive models and modify some of the inputs. For example, we may have a prediction that tomorrow it's going to rain, and we have a prediction for in terms of ozone concentration for tomorrow. But what would happen if tomorrow it doesn't rain, or what would happen if the NO2 levels are lower than predicted? Would that have an effect on the ozone level? This is something that can also be done without predictive models, and this can be useful, for example, to define policies or to evaluate the effect of some measures. For example, what happens if we limit the traffic in some areas in Barcelona, for example? Will that be beneficial for the ozone levels at some other area? Is that positive or not? So these things that can be also used or obtained with this. And finally, why is this happening? This is done by analyzing the models. We classify the inputs in terms of the strength of their association to the response, to the ozone, and also we compute the average effect of every input with the ozone concentration. So this information that is obtained from the models is extracted and is connected to the platform. And this is the final part of the workflow. So we put that information to answer the question, and finally we want also to show the results in different ways in terms of the spatial resolution. We are predicting the values of ozone at the station level, at where the air quality station is, but we are also exploring possibilities for extrapolating these results to the entire territory. And in particular, one option would be to define some prediction for the air quality areas, so one different prediction for every polygon, to these ones. And we are also studying how to extrapolate in space the predictions to have a different value or different prediction in every pixel that we're going to name this point in the future. And this is where we are now. And to end this part, I'm going to show the current version of the platform. This is our challenge, the tropospheric ozone, and this is the interface. So here we have the 4 questions mentioned before: what is happening, what will happen, etc. And we can see the information in different formats, as the air quality zones, on the individual stations. These are the air quality stations, or as a map. Well, first, let me say that this data, this information shown at this moment in the platform is not real. This doesn't come from actual records or from real predictions of the models. This is just for demonstration purposes. So we're just showing some numbers that don't have anything to do with well, reality with predictions. But well, you know what is happening if we click on some station, we have well different information. In this case, we have the average number of episodes of high ozone concentrations per year in different stations. This is one of the plots that we are developing. Regarding what will happen, these are actually the predictions, or will be the predictions of our model, and we can select which output to show, either for tomorrow or the day after tomorrow, and either numerical or categorical results. So we can see how we can just check the name of the station here. We can show this same information associated to the air quality areas, or we can draw a map that will be based on the particular values of every air quality station. And we can go to the what would happen if, what if scenario. This would be the actual values of the inputs, and here we will be able to modify something. For example, the wind velocity. What if tomorrow the wind velocity is 0? Then we can recompute the predictions of our model and check the updated predictions. So we can well, evaluate what the difference or the effect of modifying or some of these inputs. And finally, why does this happen? When we can here click on every station and, as I mentioned before, show the actual classification of the inputs in terms of the importance of the association of to the output, to the ozone, or what is the average effect of some of the inputs, for example, the NO2, to the ozone concentration. So looking at this information, one may make decisions regarding knowing if some policy or some measure is going to be effective or not. And well, this is what we have so far. This is just, as I said, for demonstration purposes, but we already have the architecture prepared for connecting the data with the models and with the platform that we will fully develop in the last part of the project. And that's all from my side. Cecilia, I give you the floor. You're muted. Cecilia, you're muted.
Yeah, we cannot hear you, Cecilia. You have to press the unmute button there.
I'm sorry. I was saying that I have this last slide regarding strong points and weaknesses of the project. I don't know if we are already very late. So up to you, Alejandro. I mean, it's
no, I mean, there is no rush. If there are any questions or comments or opinions, I mean, feel free to ask. And if not, we'll close the session. But let's see if any of the...
So I don't know if there is any question. I think that I would pass this slide. Fernando, it's okay?
Yeah.
So,
yeah, I think it's a good idea. Cecilia has a couple of last slides that.
Yeah, but I'm not sure about that. Okay, I can show you. It's the final data that we would like to put. Let me share it rapidly. Okay, I think that it's there. Can you see it?
Yes.
Okay, so rapidly, we have identified some strong points and some weaknesses in the project. The strong points that you can see that there are more than the weaknesses. This is good, I would say. The first strong point is that we have a group that we have been able to gather a group working consolidated between the Generalitat, between CIBNE and the researchers of the UPAVE. And we have all working synergetically, and we cover all the necessary knowledge that we need for this to be a successful project. So in this, I as a coordinator, I'm very happy, and I think that all the team is very happy of this. No, we are working very well, and we are very happy in that sense. We have found in general a good quality of the data that we are using for the climate, both for the climate classification and for the machine learning engine. So this also facilitates our work. No, it's 20 years of records that we are collecting, and it's a lot of of data, and still it's a big work to work about this, but at least we have a lot of data. According to the level of scientific novelty, we've been looking for state-of-the-art papers related to ozone and machine learning, and we have not been able to find good publication that have to introduce this variable, this type of synaptic situation in the work. So I think that it can be interesting to introduce this multi-scale approach with out of the data, the models that we have, but still introducing this synoptic classification. I think it's new, and that could be interesting. And who knows, no? Maybe lead to papers or to projects, no? And actually, we have already working on a project lately. At the end, it was dismissed. The coordinator decided to stop, no, because of money issues. But it's indeed a thing that we can have and take profit of this project regarding scientific novelty. Weaknesses. Well, it would be very nice if we were able to have information and all the data that we have and that we know that are important related to this project and to ozone, which is what at the end we are working on. I'm talking regarding having more information both about traffic, because it would be important to do the different behavior of ozone depending of a weekday or not. And the same with VOCs. There is better information of emission of VOCs. So that's a drawback. And the other thing that is a weakness is that the distribution of the data that we have is not homogeneous. No, Fernando already mentioned the difficulties to fill the whole territory of Catalonia with the data that we have, because it's not homogeneous at all. So these are some weaknesses that not depend on us, I have to say, no? But the project would be much more interesting probably if we had this information. But this is what we have for the time being. And just to finish, I have to put this, they told me. So and if you have any more information or are interested in something about this project, you can talk to call Eva Pérez of GenCat or to myself. We will happy to help. And with this now, I do really finish my presentation here today.
I think Perandreu has something to say.
Okay,
Please.
let me stop presenting. Okay.
Vale. Primero de todo, felicitats, Cecilia. Fernando, también muchísimas felicidades por el trabajo que estáis haciendo. Pero quiero centrar la felicitación primero en Cecilia, porque este reto le debe mucho a su visión. Yo creo que tiene mucho mérito el hecho de plantear un nuevo enfoque para un problema complejo y conseguir unos resultados tan positivos como los que estáis consiguiendo con el enfoque que Cecilia planteaba ya desde tiempo atrás, desde el tiempo en el que ella todavía no estaba en CIMNE. Y también felicitar a Eva Pérez por compartir esta visión con Cecilia y compartir esta andadura tanto con Cecilia como con todo el resto del equipo, Fernando, desde Madrid, porque los resultados son realmente muy positivos. A mí vaya, estoy muy complacido. No sé el resto del equipo de Pixel, pero yo creo, por lo que voy recogiendo de impresiones, vuestros resultados son muy positivos. Y lo que quería preguntaros es, en adelante, ¿cómo veis, qué posibilidades visionáis en cuanto a acoplar este módulo con otros módulos que hagan previsión de emisiones a partir de modelos de tráfico u otras cosas, de manera que podamos ir reduciendo la monitorización? Porque veo que todavía depende mucho de la monitorización para hacer la previsión de los niveles de ozono. ¿Cómo lo veis vosotros esto?
Bueno, yo veo que realmente el data necesitaríamos, la verdad. Y sustituir las datas de tráfico, por ejemplo, lo veo difícil. Lo veo difícil. Lo que se nos está... Lo más parecido que podemos hacer es distinguir, poner una variable en el modelo que diga es día de fin de semana o es día de trabajo, ¿no? Eso es lo más fino que tenemos en la resolución de todos los datos de tráfico. Así que hay cosas que, ya os lo digo, estaría mucho mejor el proyecto y ayudaría mucho, seguro, tener esta información. Pero de momento cuesta mucho. Hay algunos datos, pero además cuesta mucho de que te los pasen, eso también, ¿eh? O sea, así que en ese sentido, aquí ahora lo veo diferente, lo veo difícil, la verdad, todo el tema de...
Yo, por otra parte, lo que creo en este momento, yo, bueno, antes de nada ya quería mencionar que desde luego que Cecilia es esencial en este proyecto porque de otras cosas los demás, o por lo menos yo, no tenía ni idea de lo que era, de cómo funcionaba el ozono, ¿no? Ni del interés que realmente tiene este tema, ¿no? Como ha dicho Cecilia, pues estamos preparando una propuesta para un proyecto de investigación, está claro que es un tema con interés. Decía yo, por lo que he ido aprendiendo sobre el tema, si tuviera que continuar o por empezar o que priorizar, lo daría precisamente en recoger más datos. Porque, de hecho, otro tema que ha surgido en alguna reunión es que no está claro ni siquiera el grado de representatividad que tiene cada estación. Es decir, porque sí, hay información en las estaciones de calidad del aire, pero no se sabe, muy poco, o sea, hasta qué punto eso representa, qué zona representa. Si recordáis en el mapa, hay relativamente pocas estaciones de calidad del aire, ¿no? En Cataluña. Entonces, de hecho, en el proyecto este que estamos preparando, uno de los temas a estudiar era precisamente tener una mejor idea de hasta qué punto el dato puntual de ozono representa, bueno, puede representar o no un área muy pequeña o un área mayor, ¿no? Pero yo creo que son los datos los que son más necesarios, ¿no? Porque incluso para cualquier otro modelo basado en la física, al final es necesario, bueno, pues validarlo precisamente con datos, ¿no? Entonces, yo creo que en la parte de la sensórica, que siempre en las reuniones, ¿verdad?, pues se comenta, ¿no?, que se habla de poner más sensores, que sean sensores baratos, que es complicado que sea así, pero tener más datos es, en mi opinión, lo que sería más importante a la hora de avanzar y conocer mejor este fenómeno.
Perdona, pero es que estoy totalmente de acuerdo con la necesidad de poder validar los modelos y para eso se necesitan datos, eso es incontrovertido, pero me refiero precisamente a la cuestión que comentas de cuánto de representativo es una estación, cuánto de representativos son los datos recogidos en una estación. Claro, no podemos sembrar todo todo el terreno de estaciones, tanto ya si son meteorológicas como si son de calidad del aire. Me imagino que las meteorológicas son más abundantes que las de calidad del aire y por eso pues poder partir de datos meteorológicos y de ahí inferir los datos de calidad de aire. Y por eso me planteaba si podemos sustituir o podemos contar con la modelización en cuanto a emisiones de contaminación para poder alimentar y sacar niveles de ozono sin necesidad de sembrar todo el territorio con estaciones de calidad de aire.
No sé, yo creo que se podría plantear a medio plazo, pero que antes, para tener esos modelos, habría que validarlos y en caso de tenerlos,
con esa premisa. Con esa premisa, con esa premisa.
Sí.
Sí, es complicado. Es que también desde de por sí ya en los estudios es muy complicado decidir dónde poner una estación. No es fácil. De hecho, en el proyecto lo comentábamos, en el proyecto que no fue, ¿no? Estaba un poco, de que se quería hablar un poquito de eso también, ¿no? O sea que hay mucho a hacer. Oye, deciros que esto de que decías de que venía de hace tiempo, yo el proyecto se lo pedí y se lo comenté a Eva, una cosa, hacer esta relación, cuando era un proyecto que yo estaba trabajando de freelance y le puse un precio y todo, pero me dijo que no me lo aceptó. Me dijo, no, de momento no tenim diners. Y ahora todavía no tienen diners porque se los has dado a otros. Pero bueno, la verdad es que para mí, la verdad, es un gustazo volver un poco a mi corralito, ¿no? La parte de calidad del aire y de meteorología, que siempre me ha gustado. Lo que pasa es que la vida va como va, ¿no? Las oportunidades. Y la verdad es que hemos hecho lo que yo quería, os está haciendo, pero encima es versión en 2022, porque yo lo hacía con Excel y en cambio aquí lo estamos haciendo a lo grande, ¿no? O sea que en ese sentido va súper bien y la verdad el trabajo con Machine Learning, con Fernando y su grupo es impecable. O sea que acá, la verdad estoy muy contenta en todos los sentidos. Ahora que realmente acabe bien, es lo que estamos haciendo. Bueno,
no es para menos, Cecilia,
bueno,
no es para menos.
sí.
Hacer una propuesta en un campo complejo, como decía, y ver que pues, estás abriendo una puerta en cuanto a un campo de investigación, tiene que sentir muy bien y es muy satisfactorio. O sea, que por eso te felicito.
Bueno, muchas gracias. Pues nada. Bueno, pues espero que os haya gustado.
Sí, además quedará grabado para el que se lo haya perdido, pues estará también en...
Muchas gracias, Alejandro.
Bueno, pues si os parece lo dejamos por aquí.
Bueno.
No sé que haya algún comentario, que creo que no.
Nos hemos alargado un poquito,
Bueno, no pasa nada, ya os digo que no hay problema con esto.
Bueno.
Y nada, nos vemos en el siguiente café o seminario.
Bueno, muy bien. Muchas gracias a
Muy bien,
todos.
muchas gracias.
Venga.
Hasta luego.
Adiós.
Venga, vosotros.
Adiós.
Hasta luego.